So first of all, in this pump section selection, you have got certain theory that you have to understand. Okay. So whenever you select a particular pump or any kind of pump, you have four types of head. Okay. So one is static head.
Yes.
Increase the size with static head. And the next one is your velocity head, pressure head,
Yes.
and then it will be your static head, velocity head, pressure head, and friction head. For any circuit, if you calculate all these things, you'll get something called as total head. So total head is summation of total head is equal to summation of static head plus velocity head plus pressure head plus friction head. Understood?
Yes.
Or for any kind of circuit, all you have to calculate is static head, velocity head, pressure head, and friction head. Okay. So now let's understand what is static head, velocity head, pressure head, and friction head, and we'll work on a small problem. Okay. So that we'll understand about all these heads properly. Okay.
Yes.
So when you consider static head is nothing but the head required to work against the gravity. If you have to work against the gravity, that particular effort taken by the pump, we can call it a static head. Let me just give an example. Okay. Let's take, I've got underground tank over here. Okay. I've got a pipe that's connected from here to here. And let's say I've got an overhead tank on the top. Okay.
Mm.
Okay, so this is underground tank and this is OHT, whatever. So now let's take, if these are the dimensions, let's say this dimension is 10 feet. I'm just giving some random numbers, that's it. So this is 10 feet. This pipe from this point to this point is 10 feet, let's say. This particular one is say 20 feet, and this is other 15 feet. Now, when you take this, let's say my circuit is something like this. If my circuit is something like this, 10 feet, 20 feet, and 15 feet, automatically my static head will be just against the gravity, whatever head that is there. That is your static head. So in this case, what will be my static head in feet?
20 feet.
20 feet, obviously. So that is static head. Now, let's take another example. Okay, let's take, because of the site conditions, I had to take it something like this. Let's take, this is 5 feet, this is 5 feet, and this particular length is some 30 feet, some 30 feet, sorry, 10 feet, and from entire length is, say, for example, some 30 feet. The pipe is going downwards and then it is coming upwards. So what is the static head over here?
40.
40. Why is it 40?
Because here again 10 feet is there. 30 plus.
Wrong. I mean, from here to here, I said it's 30 feet.
Yeah.
Okay, I mean, basically, pump will be there from underground to overhead or overhead and underground.
Sorry.
Your pump is required between your underground to overhead or overhead to underground.
Underground to overhead. Right?
Overhead, right? So because of the gravity, don't you think automatically the water will come till this level inside the pipeline? Though you have a U-bend, because
Yeah.
of gravity, don't you think your water will try to reach equilibrium?
Yes.
So your actual thing is only 20 feet is your 30 feet minus 10 have to do to calculate the static head. Understood?
Okay. Yeah.
Am I clear?
Yes.
Okay, let's take
Yes.
another example. Let's take this is some 50 feet. Okay, this is anyway 10 feet only. And let's say this is again another 10 feet. And this length is 15 feet. Now, can you tell me what is the static head here? 10 feet, 50 feet, 10 feet, and all. So, what is the static head over here?
It's, it's 40 plus. That is 10 or what?
Which one? This one is it?
Yes.
Yeah, this is 10 feet of considered.
So we have to calculate till this overhead
No, you
tank
think,
level, right?
yeah, yes, obviously. You have to consider only till overhead tank level. No, you shouldn't consider it only till overhead tank. The reason is, unless in this circuit you lift the water till this point, will it be able to reach overhead tank?
No, it's like,
Then,
sorry, I didn't get what you said.
until the water reaches this top point, will the water will be able to flow into this overhead tank?
No, there is some pressure again.
Pressure, you will get some additional pressure, you get it at this point. But for
Yeah.
water to reach, don't you think it has to go till this top point?
That in
So obviously that also your pump should work. You agree?
yes.
So what will be the value 50 minutes? And that is only
40.
40 feet will be your static head in this case. Understood?
Yes. Yes.
So let's take because of some this thing. Uh, just give one more example. Let's take because of some conditions, whatever it is, I have to recirculate the pump, recirculate the piping again. I'm recirculating it inside the piping only. Let's take this as 50 feet. This is 10 feet. And this is somewhere around some, uh, let's say 40 feet. This is 40 feet. And this pipe is coming to the tank, let's say. Okay. Now I have a pump to recirculate it anywhere in the circuit. Let's say I've got a pump to pump at this location. Now you tell me what will be the static head? Let's say
Same.
resistance is some 8 feet or 10 feet, whatever. 8 feet, yeah. Now what is the value? You want me to reduce
50.
it? Just a sec, so that all the things are visible in a single page. Just a reason. Yeah. Now hopefully it's better.
Mhm.
Yeah. Now will you be able to tell what is the static head?
I think it will 50
Why is it 50?
because it is coming pump is now below, right?
Pump is below. So
From pump to till the top highest level.
pump to? No,
Pump to the
even
high.
then the value is only 40 feet. The reason is simple because here the pressure is basically going back to your tank, but the tank is open, so the pressure will be lost. You agree?
Yeah.
Okay. Now from here to here, if you see, you have automatically the water will come till here. So even though you have pump at the bottom or any location, your equilibrium will happen. The pump will get the additional 10 feet anyway. So
Yes.
additional work it has to do is only 40 feet. You agree?
Yeah.
Now, understanding static head is really crucial. That's the reason I'm giving multiple examples. Just to explain you the gravity. That's what it is.
So pump is the not a criteria from to check the static.
Pump is never a criteria for us. Pump location is not a criteria for us.
Okay.
See, because pump has to do the additional work. Because what is the pump work done? It's pressure difference between inlet and outlet. You agree?
Yes. Yes.
So inlet, you already have higher pressure there, which is 10 feet.
Yes.
So outlet, because automatically it's 10 feet, additional work, whatever it happens, that is after 10 feet you're putting. You agree?
Yes.
Understood or not? So
Yes. Yes.
that is basically your static head. So here the answer is 40 feet. Shall we go for one more small exercise? Just to
Yeah.
understand.
Okay.
Okay. Let's take the circuit is something like this. Have a tank on the top. Let's check for some reason. I'm doing reverse exercise. Okay. So water is coming down. Okay. I'm pushing it back to the pump. Let's take this is somewhere around some 50 feet. Let's take the tank height is basically some say 8 feet. 8 feet. Sorry, 8 feet. Not inches. Yeah. 8 feet. And this guy is 58 feet, obviously. Reduces length Ferraris. Anyway, 58 feet. And this is some 30 feet. So obviously 35 feet or something. And this is 5 feet. This height is 8 feet. What is it? That's it. This
Okay.
height is 8 feet, what I've represented. Am I clear?
Yes.
Okay, now you tell me this height is 8 feet, let's say. Now you tell me what is the static head?
8 feet.
It's obviously 8 feet. That's the difference between these 2 points. Understand?
Yes.
Because the
Yes.
circuit is entirely closed. Till here, the water will automatically come.
Mm.
So this example is for cooling tower. That's the reason we always place cooling tower above your chiller. If you have placed your cooling tower something like this, you will have a lot of losses.
Okay.
So cooling tower will always be placed above the chillers for this simple reason. Only height of your cooling tower will be your static head. Understood?
Yes.
Okay. Now the last example. Let's take this is a closed circuit like this. So this is also 58 feet. So this is also 30, this is also 35 feet, 35 feet, and this is also 58 feet. And let's take, I've got a pump at any of the locations. Let's take over here. I mean, water is just recirculating in the piping, let's say. For fun, I wanted to recirculate the piping. Now, what is the static head over here?
Mm. Zero.
Zero, obviously. So for closed loop systems, for example, from AHU to chillers, no matter what the height is of your AHUs at all, the static head will be absolutely zero. Understood or not?
Yes.
Clear?
Yes.
Okay. So that is nothing but your static head. So that, why is it deleting? Huh. So that is nothing but your static head. That is working against the gravity. Work done against the gravity. Against the gravity. Clear?
Yes.
Now, coming to the next one is nothing but your velocity head. Whenever a pump is running, let's say a pump is sucking, let's take this is a pump inlet and this is a pump outlet. I have one velocity at the inlet and one velocity at the outlet. You agree? And now
Yes.
there will be certain energy that will be consumed because of the change in velocity or because of providing that velocity in the circuit in the first place or not.
Yes.
So for that, we use a formula. V square, the formula is V square plus Vd square by 2G. Vs square plus Vd square by 2G. Okay. Vs square plus Vd square. Well, Vd square divided by 2G. I mean, whole divided by, obviously, whole divided by 2G into gravitation force. V square by 2G, I mean, you might have learned the formula in your, like, plus or something, right? The same
Mm.
derivation, nothing else. So V square plus Vd square by 2G will basically provide you something called as your velocity head. That generally, for our practical applications of all our MEP services, it approximately be 2 feet. 1.6 like that we get it, because generally it will be 6 square plus 8 square. Okay. The general value will be, general velocities will be 4 or 6 or 6 or 8 or something like that. So 6 square plus 6 square plus 6 square plus 8 square, right? It's just like plus 8 square divided by 2 into 32. I mean, gravity due to gravity is what is the unit? What is the value? Acceleration due to gravity is how much? If you remember, hello,
9.8 something.
9.81. That is
Yeah.
what meters per second square.
Yes.
So this particular one is 6 FPS and 8 FPS is the velocity that we are considering,
Yeah.
right? So when you consider the 6 FPS and 8 FPS, I have to convert this 9.81 into 9.81 into 3.28
Fits.
because that's all I realized in feet per second square.
Yeah.
So for that reason, we are getting this divided by 32. I've done it. Clear?
Yes.
So approximately 1.56 like that we get it. But instead of 6, it could be even 4 and 8 also sometimes. 4 FPS and 8 FPS we do it. Then also it will be the similar case. Understood? So for that
Yes.
reason, generally we take 2 feet as a round off value instead of doing all these exercises. Am I clear?
Yeah.
Then coming to the next one is pressure head. So what do you mean by pressure head is what is the pressure required by the system? That particular one you simply call it as pressure head. I'll just give an example. Are you aware of hydropneumatic systems?
I heard of it, but
Okay, so hydropneumatic system means when the building is tall, we
yeah.
don't use any overhead tank. Instead, we have a pumping station in the pump room itself, which is adjacent to your underground tank. Near the underground tank, we will construct one more room, which we call it as a pump room, where you have all
Yes.
your fire services and all. Well, you said you're already working, right?
Yes.
So, if possible, just go anytime. Where do you work exactly? I mean,
Sorry.
if it's okay. No, where do you work?
In Mangalore only.
Bangalore. Is it a tech park or something like that?
No, no, it's like a consultancy. MEP.
No, no. The building, is it in tech park or something?
No, no, it's like projects are based on this Middle East projects.
Okay, what I said is, where is your office located? Is it a simple small building or
Yeah,
is it
simple
a
small
like,
building. Yes, a simple small
oh,
building.
oh, okay, okay, okay. No, if it's a bigger one, I thought I'll suggest you to go to the plant room and observe all the components. Even chillers also, you can see it actually. That's the reason,
Yeah.
nothing else. Okay, that's okay. So, in
Pump room,
such
I
kind
have
of
some
build,
idea because since I worked inside.
right, you might have seen at a lot of locations.
Yeah.
So anyway, so adjacent to that pump room, you have some, yeah, I understand that you know that, but for you to understand all the components and if you can get back to me with queries, I guess it will be much more practical for you. That's the
Yeah,
reason.
I got it.
So where do you go? Mangalore, you said, right?
Yes.
Okay. If you're planning to Bangalore sometime,
Okay.
okay, you speak with Mr. Sunil. He'll arrange a site visit. I mean, if it's possible,
Okay.
so that he can explain you to any of the sites if possible. That's again the day when you're going to come. But
Oh,
anyway,
okay.
so in this case, what will happen is we'll have a pumping station, and from the pumping station, you will directly pump it to all the taps and all your faucets or like whatever. location it's required. Understood? So
Yes.
for that case, basically, when you consider your pump head, I mean, if you wanted to consider your pump head there, so there at the tap, if you just have atmospheric pressure, will it be sufficient?
No.
Like you should have certain pressure, like 1 kg or 0.5 kgs. Yes or no?
Yes.
So at the terminal and whatever pressure that is required, you simply call it as pressure head in our example. Understood? At the terminal and whatever pressure that you have to minimum maintain in the system, that particular pressure, you simply call it as pressure head. That is nothing but the pressure required in the system at the terminal point, to be precise. Am I clear?
Yes.
Okay, that is your pressure head. For example, if we consider pressure required. Yeah. For example, if you design as per NBC code, at any point of your hydrant system, you require minimum 3.5 kgs per second, kgs per centimeter square. Understood?
Mm.
So there your pressure head becomes 3.5 kgs. Understood or not?
Yes.
So at the terminal location, whatever pressure that is required, that is nothing but your pressure head. And the last important thing is basically your frictional head. Frictional head is due to friction, whatever it causes, the head loss. That particular one you'll count under frictional head. For example, whenever a pipe is reducing or a pipe is increasing, or like you have an elbow. So whenever or when a pipe is straight, also, then do you think it will absolutely be frictionless? There'll be certain
Yes.
amount of friction between water and the
Yes.
surface. You agree?
Yes.
So that particular thing, we simply call it as friction. Because of friction, whatever effort it takes, you simply call it as frictional head. Am I clear?
Yes.
Okay. Now coming to the next one is how do we calculate a frictional head? Okay. So yesterday, if you remember, in pipe sizing tool, we understood something called as your frictional factor. We have
Mm.
calculated.
Yes.
So using that itself, we'll calculate the frictional head. So frictional head per 100 feet, you got the factor. Multiply by the actual length. If you do it, you will get the actual friction. That particular thing also you'll add it. So this is due to friction. Due to friction. That means if you have a valve or strainer, whatever it is, everything will be covered under this frictional head. Understood? So
Yes.
if you add everything, you will get the total head. And once you have the total head and you know the flow rate, then you will be able to assess something called as brake horsepower,
Yes.
BHP of a pump. So brake horsepower of the pump is equal to, generally, the formula that we use is
You
brake horsepower is equal to total head into flow rate
flow.
in GPM, total head in feet, okay?
Yes.
Total head in feet multiplied by, you were telling
Mhm.
something, sorry?
Yeah, that formal only.
Okay, okay. Flow rate will be in GPM, 0 into efficiency, 3960 into efficiency. So this will give you the total brake horsepower. Horsepower is equal to your brake horsepower plus drive losses. Brake horsepower plus drive losses. That will generally be if it's a belt driven. Nowadays, it's not belt driven. At least for pumps, it's never belt driven. We'll directly use direct driven. So we'll take some 5% loss because the inertial loss of the coupling or coupling eccentricity loss or something. So you can, instead of adding it, you can directly multiply it. Brake horsepower BHP into 1.05, you can take it. That's adding 5% to it.
Mm.
Understood?
Yes.
That will give you your HP. And then you can convert into, from HP, you can always convert into kilowatts, alva.
Yes.
Yeah, that's simple. So you can roughly estimate what is the kilowatts required by the pump motor as well. Clear?
Yeah.
Okay. Now let us understand about this pump head calculations. Okay. Tomorrow, day after, once we complete the pump selection, then I'll explain you about impeller sizing and all roughly to estimate. But again, practically you don't require 90% of the time, but for knowledge wise, at least it's on. I mean, uh, you'll understand the principle of the pump better. That's the reason.
Yes. Mm.
Okay.
Yes.
So now what we'll do is we'll try to calculate what is the head that what is the value that we require. So let us understand this. Now we'll work on a simple problem of overhead tank and underground tank. Is it
Mm.
okay?
Yes.
No, it's not a part of HVAC, but it'll be easy for us to use. Let's say I've got a piping system, something like this. 25. Yes, the tank size is huge. Let's take, I've got a pump. So I've got a piping which is going across like this. And then I've got my overhead tank, underground tank, and similarly I've got my overhead tank as well. Okay.
Mm.
Overhead tank always it will be at the top, you'll provide this supply rate. Agree?
Yes.
Okay. So this is your underground tank and this is your overhead tank. I'll just give the numbers. UGT underground tank is a text. I didn't edit the size anyway. 300 something. So this is your underground tank. This is your OHT overhead tank. OHT. Let's take an example. OHT, say for example, some 20 KL, 20,000 liters.
Okay.
Is it fine?
Yes.
The value is 20 KL, and let's say I have a pipe again. So let's say this pipe is basically having a flow rate of. Let's take an example. I have a pump anyway. Let's take I have a pump at this location. So you're comfortable with CAD and Excel sheet, right? Instead of using pen and paper. I mean, instead of iPad, I'm
I'm
using
comfortable.
this.
I'm
This,
comfortable.
this is it. Right? Okay, good. So at the inlet, I'll definitely have a butterfly valve
Sorry.
in case
Yeah.
of this. Right. So obviously, I'll have a butterfly valve
Yes.
at the inlet. So this I'm considering as a butterfly valve at the inlet, and definitely I should have a strainer because whatever the fluid that is there, that needs to be cleaned before the or else impeller can get hit and it can it can lose your head properties. You agree?
Yes. Yes.
So let's take I have got a vice trainer. It's the symbol of the vice trainer. We anyway use it everywhere. Okay, let's take this is your vice trainer. I'll use it. Yeah, so I've got a vice trainer. Okay, flexible belows and all you can you can need not worry. And then at the pump outlet, it's mandatory for you to install something called as a non-return valve, NRV. Understood?
Yes.
The reason why you require NRV is basically whenever you have a water, it should not flow back again to your tank because of the gravity. You agree?
Yes.
So for that reason, it's mandatory for you to provide a NRV, non-return valve. So
For
it's
any
will
pump.
always for any pump, it's mandatory. Yes. Not only for HVC, any pump, the minute you provide a pump means this assembly is constant always,
Okay.
with respect to the type of application. So this NRV will allow the fluid in this direction, it doesn't allow in the opposite direction. And one more butterfly valve at this location, right? So these are the points that I have it. So this is nothing but our sizing. Now what we'll do is we'll try to calculate what is the pipe size, what is the flow rate, each and everything we'll try to do it. Okay. Now, when you consider 20 KL, let's say, within how much time you want it to be filled?
Mm.
You tell some number. I mean, within how much time you want it to be filled? I mean, don't tell it in 2 minutes, 3 minutes. Obviously,
No,
that's
it's
awkward.
like it's
Yeah,
1 hour time.
within 1 hour time. Okay, perfect. So you wanted to fill it in 1 hour's time.
60
So if you
minutes.
want to fill it in 1 hour time, so 20,000 liters divided by 60, don't you think I'll get LPM?
Yes.
So 20,000, 200, 2,000, 20,000 divided by 60. That will give me 333 LPM. You agree?
Yes.
So this value is 333.3. So I'll take 334 LPM.
Yes.
So this value is 334 LPM. So if I want to convert into gallons, I can directly divide the value by 3.78 because I'm more
Okay.
comfortable in gallons. It's the reason, nothing else.
Yeah.
So what is the value? 334 divided by 3.78
334.
divided by 3.78 because 1 gallon is 3.78 liters.
88.5.
88.5
Yeah.
GPM is the value. I mean both the units I'm writing it. Okay. Okay. So these are the flow rate that I should have for the pump. You agree?
Yes.
Now let's take the this one. Let's take our charts, or I'll use software instead of a chart now because you already understand how to use software. I'll share you this tool as well. Okay. And by the way, you use Telegram by any chance?
Telegram I don't use.
Can you download it once? Because all the setup files and all, no, in WhatsApp, I don't think it will go.
Okay.
So either Telegram or any of the things we have to use it, or else through Drive, I'll try to share it, Google Drive or something. Let's see.
Okay.
Even duct sizer, everything, I have to use this tool. That's the reason. Yeah.
Mm. Okay.
Okay. So now this particular is a pipe sizing tool that I use it. I mean, instead of charts, we can use it simple. Now the temperature of the water will be somewhere around some 70, 100 or 120 degrees on this. So 70 degree Fahrenheit or something.
Mm.
Okay. I'll take a Schedule 80 plastic pipe. Fine. Now what is the flow rate that I require? 88.5 GPM. 88.5 GPM. And the size of this, let's say, is 2 inches. 88.5 GPM means the velocity head loss is way too high. You agree? 14. Is it
Yes.
acceptable?
No.
No. So let's take some 4 inches. How much? 334 alva?
Yes.
334 GPM. So then also the head loss is way too high. Generally, for plumbing applications, we will consider the velocity as 6 FPS maximum. And friction factor, same, it should not exceed more than 4 feet per 100 feet. Understood?
Yes.
6 inches, let's take 334. Okay, here head loss is very less, velocity is also 4, so I can probably make 5 inches pipe. Oh, 88.5 alva, shit. Why am I doing for 334?
334 is
334
LPS.
is LPM,
LPM.
here the
Yeah.
units is GPM alva, sorry, I'm really sorry.
Yes.
So 88.5 means I can have a lesser size only. I can have probably your 3
3 inch.
inches pipe or something. 88.5.
Mm.
So head loss is 4.2.5. I can actually have even 2 also probably. Let's see. 50 mm dia, 88.5. No, this is quite high, so I have to go for 3 inches pipe or 2.5 inches. 88.5 alva, 88.5. Here also the head loss is more than 4, so we'll go for 3 inches only. I don't have any other option. 88.5 GPM if you take it, the value is 4.3 and head loss is 2.157. You agree?
Yes.
So fluid velocity, what is the units? What is the value? It's like someone try to interpret it.
2.1.
Just a second. But, okay. Someone tried to enter about nothing. So, take it. So here, what is the friction factor that we got? Friction factor is 2.157 per 100 feet. 2.157 per 100 feet is the value. And what is the velocity we have considered? Velocity is 4.3. So this value is 4.3. 4.3 FPS. Alva?
Yes.
This is the value that you got it. Of course, we didn't give the pipe dimensions. That's really important. Right, let's take this dimension is, for example, some 20 feet. Is it okay? From
Okay.
here to here, it is 20 feet. From here to here, let's take is some 50 feet.
Yeah.
From here till the top. Okay.
Okay.
And let's take this value is some 30 feet. Just give some random numbers, I agree. So this is the value that I'll consider. Is it okay?
Yes.
Reduce the length so that circuit I'll be able to do it. Okay. So this is the total volume that we have there. So now we have to select what is the head required for this pump. That is a tank. Am I clear?
Yes.
Okay. Now we'll go to a problem. Okay. Shall I delete this? I guess you understood, right? You made a note or you did not?
Yeah, I know.
You made a note, right? Okay.
Mm.
So now let's convert these, let's calculate all these values. So now static head. So what is the static head here? That is against the gravity. So
Oh,
against the gravity is how much here?
50.
50 feet. So automatically, this is 50 feet is a static head. You agree?
Yes.
Right. Slide is not coming. It's there, but it's not visible. Hmm. No, no. Computer is symbol it's shown. Yeah, that's okay. So this is static head is 50 feet. Now I have to worry about the next one, which is your pressure head. What is the pressure head that is required? Should I have any pressure near the OHT for water to come in?
Yeah. Yes.
Why do I require atmospheric pressure also? It will just because it's open piping, automatically it has to release water into the overhead tank. That's ಅಷ್ಟೇ ಅಲ್ವಾ?
Yes.
Do I have to have an additional pressure? Like 1 kg,
It's
2
not.
kgs, do I have to maintain?
No.
It's not required because it's open piping. At the end of the day, the valve gets open and it will go. You
Yes.
agree?
Yes.
Of course, you might have a float valve. Float valve will require very little pressure, so that you can consider certain value. But anyway, in our case, we'll take 0 in this
Yes.
example.
Okay.
Okay, but anyway, generally you have a float valve here.
Yes.
You have that ball kind of thing, but that will require very minimal pressure because whenever the water level is not there, it will automatically open due to weight of the ball cock.
Yeah.
So you need not practically require any pressure. But anyway, we take factor of safety in that everything will be coming. So don't worry. So anyway, pressure head I can take it as 0,
Yes.
0 feet. Now coming to the next one is your frictional head, which is really important. So frictional head, I'll try to calculate it separately. Frictional head. Okay, velocity also will do it anyway. Frictional head. Okay, this is total head. Pump selection. So here, the next one that you have is something called as velocity head. Velocity head. So when you take velocity head, v square plus vd square by 2g. So in this case, it's only constant velocity I'm considering. Practically, generally, you inlet you have a bigger diameter and all. But anyway, currently I'm not bothered about it. Instead of directly I'm taking 2 feet. Shall I take it? I've already explained you. I mean, v square plus vd square by 2g approximately will take 2 feet as a value.
Mm.
So I'm directly taking this value, but you understood the derivation, right? V square plus vd square by 2g.
Yes. Yes.
Okay. Now coming to the last one is your frictional head. Frictional head. So frictional head, we will calculate frictional head due to straight pipe, due to straight pipe, due to pipe fittings, and then due to pipe accessories. So pipe fittings means your elbows, reducers, increasers, all those things. Your
Yes.
piping accessories are like your your butterfly valve, strainer, all those things. Okay.
Mm.
So we will calculate because of all these elements. Okay. So because of straight pipe, we'll initially try to calculate. So when you try to take your your these things, which is straight pipe, I can directly take the total length of the piping and then we'll calculate it.
Yes.
So total straight pipe. So friction due to straight pipe. Friction due to straight pipe. So friction due to straight pipe, how will you calculate, is equal to total length of the piping. That's 50 plus 30 plus 20 is how much? 100 feet. You agree?
Yes.
Okay, to make it between, I mean, slightly change. Shall I make this as some 30 feet again?
Okay.
And this I'll take it as 40 feet. Because 100, it will be cancelled. That's the reason. I think, of course, you can have that also. But anyway, now what is the total length of the piping that you've got it? 50
120.
plus 40 plus 30,
120.
120 feet. So 120 feet is the length of the pipe. Then
Yes.
friction factor is, I mean, this is length of the pipe. What is the friction factor?
This was
2.157 per
2.157.
100 feet.
Yes.
2.157, so is equal to 2.157 feet per 100 feet. You agree?
Yes.
Some brackets, I'll write the units anyway. And this is feet per 100 feet, alva. Okay. Now total friction, how much it will be? Friction headed due to straight pipe. So this will be is equal to this into this divided by 100. You agree?
Yes.
So this will be your friction factor. Your actual value due to straight pipe will be this one, 2.55 feet. Understood?
Yes.
Then don't you think we have to calculate because of your elbows, all those elements?
Yes. Fittings.
So due to friction due to friction
Fit-
due to
Fittings.
not friction, I should say head due to frictional head due to FHL, right? Now it will be frictional head due to pipe fittings. Friction head due to pipe fittings. So your pipe fittings means what all things will come into picture?
The elbows, reducers,
Yeah,
and
elbows, reducers, all those things will be your fittings, right? So now
yes.
in this case, I did not consider any reducer. We'll take only elbows. So in
Yes.
our case, because it's a simple circuit, can I take only one elbow and two elbows over here?
Yes. 12.
Of course, when we do tomorrow on a practical problem of HVC, you have a lot of elbows because we'll work on one complete HVC layout. I mean, with all the AHUs, everything, so that will calculate everything. So currently, we'll take only our this thing, which are two elbows. So I've got two number of elbows. You agree?
Yes.
These are the only this elbows. So now what I have to do, I have to calculate what is the value. So that also we got it in data due to heat load. ಅಲ್ಲಿ ಇರುತ್ತೆ. ಒಂದ್ ನಿಮಿಷ. And so if we take this thing, so in this case, again, we can go to the accessories. Of course, compared to this, the better approach is you always try to get it from the manufacturer. Okay, manufacturer will provide you. I'll show you that method also, don't worry. Okay.
Okay.
So here, basically, I have got something called as a vice trainer. So, oh, sorry, not trainer. We are taking about elbow salva. Really sorry. So this is our five losses that we have it. So 90 degrees standard, if you take it, what is the diameter of the pipe? What is the diameter of the pipe?
Pipe size is 3.
Oh, we didn't do pipe. Oh, I didn't mark pipe. Oh, it's 3 inches.
Yes.
That's 80 dia. You agree?
Yes.
I didn't mark it really, sorry. Percentage C. So generally, you've got 3 inches means 75 mm. 75 is not available, so you'll go for 80 dia. You agree?
Yes.
So for 3 inches size, if you take it, the equivalent length is 7.5 feet. So there is a concept called as equivalent length. So what do you mean by that? Like, this particular equivalent length in feet is basically the one elbow is equal to 7.5 feet means whether you use one elbow or you use a straight pipe of 7.5 feet, you will have equal losses. Understood?
Yes.
So now value is, so now what we'll do is how many number of elbows are there? Two elbows are there. So we will use a we'll use a small chart kind of thing. I guess that will be better.
Okay.
So I'll do one thing. Instead of doing this exercise, I'll write friction height due to pipe fittings and accessories.
Yeah.
So that I'll write here. So I'll write serial number, description, description. I mean what it is basically, and then after description, I can go for I'll delete this guy over here. Yeah. So after description, just a sec. I'll go for this. Mhm. I can go for description.
Yeah.
But later on, it will be confusing why gaps are up. Yeah, take it. So this is description, and after description, we have got this one. What do you call uh, uh, equivalent length, diameter, equivalent
Yes.
length,
Yes.
equivalent length. Then it will be total numbers, so numbers, then total length. Then I can write it as numbers total length. That should be fine, or actual length, whatever it is. Sorry, numbers. I have to write friction factor. That's more important, alva. Yes or no?
Yes.
So friction factor. I'll take friction factor, then equipment. Sorry, equivalent length. Then it will be numbers. Then it will be total length. Understood?
Mm.
It is Alt HW, Alt HW. Yeah, HW. Okay, now serial number one is what is serial number one? Elbows. You agree?
Yes.
What is the diameter? 3 inches, 80 mm. You agree?
Yes.
What is the friction factor we got it? 2.157 per 100 feet.
2.1%.
2.157. This is per 100 feet anyway. So what is the equivalent length? We got it from the chart, which is 7.5 feet, alva. Illi.
Yeah.
So you got 7.5 feet. How many numbers are there? Two elbows are there. One at the bottom and one at the top. You agree?
Yes.
So these are two numbers. So total length is equal to this into equivalent length, sorry, AB into friction factor divided by 100. You agree?
Yeah.
So automatically 0.3235 feet is the total value. I've got it. Understood?
Yeah.
So what I've done is the total equivalent length into numbers. I'll get the total length multiplied by friction factor divided by 100.
Yeah.
Got it?
Yes.
Coming to the second one is I've got butterfly valve. Agree?
Yes.
Butterfly valve. Dia is again 80 mm. That's 3 inches. Now I have to calculate and how many are there? One at the inlet, one at the outlet. You agree?
Yes. Two.
So I've got two numbers over here, and then I've got friction factor will be same. I'll get equivalent length from the charts again. Okay, but don't worry, this charts also we don't use it. Practically, what I do is I'll directly take it from the OEM.
Yeah.
Manufacturer will provide that tomorrow's lecture I'll teach you how to get the values from OEM's chart. Okay?
Yes.
So I'll take my butterfly valve. So your butterfly valve is nothing but your this thing. What do you call your gate valve? Okay.
Yes.
But butterfly valve is different, gate valve is different. But anyway, we have the nearest one is gate valve that we have it. That's the reason. Okay.
Yes.
So when you take this butterfly valve here, you have something called as your butterfly valve. What is 3 inches? What is the equivalent length? You have got it?
3 inches. 3 point.
Hello. I'm audible now? Okay. So
Yes.
somehow Bluetooth got disconnected and then again it got connected. That's some confusion. Anyway, so what is the equivalent length over here for the gate wall? It's 3.2 feet, Alva.
Yes.
Not it. So this is 3.2 feet. So your total value will be same formula. I can use it.
Yes.
Control D. So automatically I got this value. The last one that I have is your NRV, non-return valve. So your non-return valve is nothing but your check valve. Check valve for 3 inches. The value is 30 feet is your equivalent length.
Yeah.
Okay. So this is also 80 dia. So friction factor will be same. And this is 30 feet is your equivalent length. How many numbers are there? Check valves?
One.
One number, controlling. So you got this one. So total losses due to all these piping accessories is how much? Sum of all these elements I can do it. Do you agree?
Yes.
So 1.10, 1.10869, whatever. So now what we have to do, we have to calculate whatever is the value. So total frictional head. Frictional head is equal to total frictional head is equal to how much? Due to straight pipes and due to accessories. You agree?
Yes.
So automatically we got this value, which is 3.69. So here in this pump selection, I'll directly consider I'll link it from this guy to this guy over here.
Mm.
Feet. So everything is feet anyway. Yeah. Now your total head is summation of all these heads. That's it. Total head is summation of all these heads. Sum of all these heads. I'm not taking FOs here. Practically, we take some 10% as factor of safety. Am I
Okay.
clear?
Yes.
Now coming to the next one that we have is this is feet again. Then coming to the next one is your brake horsepower, BHP. What is the formula? Is equal to total head into
Flow.
flow rate. What is the flow rate? 88.61 alva?
88.5.
88.5, sorry. Into 88.5. Into
Yeah.
88.5 GPM divided by, or I'll write it here, I guess that will be better. This is flow. This is total
Total head.
head. Total head. Then I'll write efficiency of the pump. Efficiency of pump. So flow is how much?
88.5.
88.5.
Yes.
88.5 GPM. Total head is how much? Is equal to 55.69, whatever decimals the value is. And then pump efficiency. Your pump efficiency generally you will take around 70%. 65 to 70% you take it. Clear? Okay, so you take 70%. So your brake horsepower is equal to your flow rate into head divided by what is the value? Uh, 3960 into efficiency. 3960 into efficiency should be in percentages. This is 70% alva.
0.7.
So 0.7 I have to do it. So is equal to this value divided by 100 again. You agree? Yeah. So it will be 1.77 HP brake horsepower. So HP is equal to how much? Is equal to this into 1.05. That's because of drive losses. Totally 1.86 HP motor is what you require. Am I clear or not? Understood?
Yes.
So this is a short note on your pump selection for this particular application. But again, when you require, for HVAC, it will be a bit detailed where we'll try to understand different kind of valves and all, whatever you have learned in chillers. We'll apply everything there and we'll work on a practical problem. Clear?
Yeah.
Done? So we'll continue from tomorrow again.
Yes.
Okay, fine, man. Today. So tomorrow again, we'll try to wake up a bit early because we can spend some time. That's it. Nothing else.
Okay.
I mean, I can take for longer duration, Alva.
Yeah. Okay.
ठीक है
Yeah.
fine fine bye good day